We will learn a lot about Triton kernels, about GPU CUDA kernels of DeepSeek, and how to represent numbers in FP8 in lower memory using these CUDA kernels. So this is the file, it's kernel.py by DeepSeek, and let's understand all of this stuff. You can find this file at GitHub DeepSeek v3 repository. So a kernel is a function that runs on GPU, not the CPU, and it is executed in parallel across many threads. It's like a function that will run simultaneously thousands of times, each time on a different piece of data. That's a kernel. So in Triton, the programming language, a function decorated with @triton.jit, just in time, becomes a kernel. This is an example. Let's just see this, and this is the function, and that's what we need to see. So using a kernel, you can run massively parallel operations on the GPU. For example, if you want to add 1 to every element of a 1 million element array, on CPU, it would loop over array elements one by one and add 1 to each element, while on GPU with kernels, you can launch thousands of parallel threads, each adding 1 to a separate element at the same time. Let's just try to understand a bit of code. Even if we don't understand it 100%, it's good just to see what we can understand for the first time. So PID, each kernel instance or thread block gets a unique ID. Then we have some offset, PID times block size plus TL.arrange. So each thread accesses a block of data. Then we will load data from global memory. So this X is a pointer to the tensor in the memory. And we will store the result by multiplying this X with 2 to get Y and store that result in the memory. So these are the key concepts. So the kernel is our function, our entire function that's denoted, marked with this decorator, code that runs on GPU. So we are writing it in a Python file, like kernel.py, and then marking it with this decorator so it gets converted to a kernel and runs in GPU. Then each kernel instance, so if we run a kernel multiple times in parallel, each instance has its own unique ID. Then we have loading from memory, tl.load, and then passing the pointer at the memory. Store, so pointer where to store in the memory, in the GPU memory, and the value you want to store. And we have some optimizations. So what would you write inside a kernel? Only operations that Triton supports. Think low-level tensor arithmetics. So allowed, arrange, load from memory, store to memory. Arithmetics like plus, minus, times, divided. Dot product, sum, maximum of the array. Mass, conditional logic. And what are not allowed things? Python loops. So when we are writing Python code, inside of this function, we cannot write Python loops, not allowed. Imports, like NumPy, PyTorch, and Python function calls. So you cannot call a Python function from this kernel. So when you compile this code, it gets converted from this Python code to PTX and SAS. So PTX, parallel thread execution. This is intermediate level code. It's GPU agnostic. It doesn't matter which architecture or GPU you are using. And then that gets compiled into SAS, which is a low-level final code, machine code for the GPU. And it is specific. There are specific versions for specific GPUs. So SAS is a streaming assembler. Assembly for NVIDIA GPUs. And we are just talking about NVIDIA GPUs now, by the way. So it's agnostic across many NVIDIA GPUs. And this SAS is for specific NVIDIA architectures like Hopper or Ampere. So PTX is an intermediate assembly-like language for NVIDIA GPUs. It's what you get after compiling CUDA code or Triton kernels, but before the GPU hardware sees it. It's virtual ISA, instruction set architecture. It's not tied to specific GPU hardware. So, it's abstract hardware details, abstract hardware instructions, and can run on different generations of GPUs. Human readable, sort of. So this is an example. Does look a bit tough, but I can see that this is like maybe float 32. Maybe we could understand it if we ask ChatGPT to explain. So it looks like we are adding using float 32 addition here, and we have maybe one variable, two variables. I'm not sure what this is, but we have some maybe global memory here, loading from global memory. Maybe this is the address, the pointer. So, but I think we don't need to understand this. We just need to understand CUDA code and kernel. I mean Triton code. We don't need to understand this. And then what is SAS? SAS streaming assembler. This is the real final GPU machine code. It is specific to a GPU architecture. For example, SM90 for Hopper and SM80 for Ampere. It's generated by compiling PTX with NVCC or PTX-AS, maybe that means assembler. So it's not portable across architectures and can differ significantly across GPUs for performance tuning. So I guess across GPU architectures, very low level. Analogy, PTX is like Java bytecode and SAS is like native x86 machine code. This is the compilation flow, CUDA Triton kernels to PTX to SAS. You can actually see them by running these commands if you want. Now let's talk about Triton runtime. Triton runtime is a system that takes your Python-defined Triton kernels, compiles them, just-in-time compiler, optimizes them, and runs them efficiently on NVIDIA GPUs. So it's especially efficient for custom matrix operations, deep learning workloads, and low-level tensor manipulation. And that's it. Now let's see the difference between coding in CUDA and coding in Triton. So CUDA, you are using C++ with CUDA extensions, and Triton, you are coding in Python with Triton decorators. So here you have Triton decorator. In CUDA, you need to manage memory manually, device allocs, sinks, and in Triton it's automatic via PyTorch tensors. So you should know, I think, if you code in Triton, basically it's a lot easier than coding in CUDA, and the performance is just a little bit worse, maybe a few percentage worse. So people choose more to code in Triton. However, I know that DeepSeek's employees used some did some coding in CUDA to extract even the latest bits of performance. But also I see a code written in Triton as well from DeepSeek. So the reason you wanna write kernels either in Triton or CUDA is if you have multiple operations, like you have some addition and then multiplication and then activation function, every time you need to send the data into GPU, do calculation, send back, then back to GPU calculation, then back. So a lot of the time is spent on sending data back and forward. So you write a Triton or CUDA kernel that's gonna do all of those calculations at once. So you just send data once, do all of the necessary calculations, and then return the data. So that's about saving memory bandwidth. And then further optimizations that DeepSeek employs are this FP8 quantization, where they are also quantizing data from 32-bit or 16-bit numbers into 8-bit numbers. And then they further reduce the memory bandwidth necessary so they can send even more data back and forth within the GPU. So you can watch this video on my channel. These are just example code of CUDA in C++ and Triton Python. So I don't think we're gonna be I mean, we don't need to spend time understanding this. You can just quickly take a look. So both of them are adding functions, but I'm not sure exactly what they do. Ah, yeah, so you pass in the pointer for the first number, the second number, or I think it can also be array maybe. And then this is where to save the result, at which uh, memory space. So this is also pointer here, z pointer. So it stores memory. Okay, let's move on. Also important, CUDA is for general GPU programming, and Triton is mostly for tensor programs, so about neural networks and stuff. So custom deep learning operations. Yes, you can use it in CUDA, but very hard to write. In comparison to Triton, that's a lot easier to write because it's made for custom deep learning operations. So let's say you want to write custom FP8, the general matrix multiplication. But so the what we wrote last video that I showed you in CUDA, it would be more complex. You would need hundreds of lines of code, warp, synchronization, memory alignment, styling. So you need to do this manually. While in Triton, maybe 30 to 50 lines of code or even less. And you can use these dot product load for memory, store to memory, arrange the array, etc. Then we also have this Triton.pointer. So this is a low-level abstraction representing a pointer to a tensor in GPU memory. It's how you access and manipulate data inside a Triton kernel. So using this pointer. It is not a concrete Python object you manipulate directly. So you do not manipulate it directly. When you write a Triton kernel like this, so you have Triton decorator and then define kernel x pointer, and then you can use it to load from memory. So x pointer is of type Triton.pointer, which means a pointer to memory on the GPU that you can read from or write to inside of the kernel. And then what is this offset? So we have pointer plus offset. We are loading data from there. So let's say we have an array 10, 20, 30, 40, 50, and offset is 2. Then pointer plus offset will point to the element at index 2. So it's going to be this number 30 because this is index 0, 1, 2. So it loads, so this load pointer plus offset loads the value of 30. So remember that this pointer is pointing to the entire array, and offset will select which element in the array. Now let's suppose we have some other pointer, so tensor, so this is x pointer is pointing to this tensor, and then we have offset as an array. So we use TL arrange, so 0 to 4, which will get us, this will get us elements 0, 1, 2, 3, and we will multiply each element by 4, so we will get 0, 4, 8, 12. So now this is our offset. Instead of a single number, it's a vector now. So now when we say load from memory this pointer tensor and offset, we will get elements at 0, which is 10, at index 4, which is 20, index 8, and index 12. And that's going to be our x now. So you can look at this offset as shifting the memory place at which this is pointing. So if we are pointing at 0 here and we have offset of 4, then it will point to the 20. And now we will read the 20. If offset is 8, then it will shift this point at 30. So this is another example here. If we have pointing at memory place 1000 and offset 5, if we add them together, so you see here x pointer plus offset, then this first place, these two will be added and it will point to memory memory place number 1001, 1005. Here are some commands. So tl.arrange from 0 to block size. This will create a tensor that has block size -1 elements, and the values will be from 0 to block size -1. So we have this absolute value. It's gonna take element-wise absolute value of this tensor array X. So it will just make each element positive. Here we have storing the memory. So we have pointer and offset. So to calculate the place at which we will store this value. Then we can get maximum value of a tensor. If I go here and search for max, we get here maximum value of the absolute tensor, absolute values. Then we can create tensor all zeros. So it will fill them with zeros. We are using that for accumulators. So it's gonna be block size m times block size n. It's gonna be a matrix of these dimensions. And D type is 32, float 32. As I mentioned, we are doing accumulation of the results, calculation results in 32 bits for precision. Then we have these, let's say, dot product here. And we also have float 32 type and this float 8 exponent form mantissa 3 finite only type. I explained this in the video I mentioned. Then there is also this mask that will that is a Boolean mask to controlled valid memory access, used to prevent out of bounds access when dealing with edge blocks. So I guess edge blocks. So if you have a tensor, you divide tensor into blocks or subparts. You don't wanna go over the last block and go out of bounds. So that's why it uses this. You can use this mask. Or that's my understanding, at least I think. So let's look at this piece of code. So let's say we have M5 and N6. So we have this matrix of shape 5 times 6. And we have block size 4. So that means we will going to divide the matrix into 4 times 4 tiles. But the bottom right tile, which starts at row 4, column 4, will go out of bounds because the matrix ends at row 5 and column 6. So this would be the mask for the block that I'm talking about. So the block in the corner where there are only, there are only numbers at the 5th row and 6th, 5th and 6th whole column. So in this corner block that's after 4, 4, so the block still is 4 times 4, but because the whole matrix is 5 times 6, then this corner block will just have these two values here. So we want to create a mask that has true only at these places where the values actually exist, and false. So this would be position 5 times 7, which doesn't exist because our matrix is 5 times 6. So these are the calculations. I can start from the top here. So maybe I will just scroll this for you if you want to take a look. So this is how the masks are calculated. So basically we have this formula, and offset M is 4, 5, 6, 7. So these are because this is our tile. So the first tile in the was 0, 1, 2, 3 times 0, 1, 2, 3, and then this tile is 4, 5, 6, 7 times 4, 5, 6, 7, and we actually only can go up to 5 for M and up to 6 for N. So actually this is a bit confusing. Anyways, I'll just scroll this for you if you want to check. And true and true, true and true, true and false, true and false. So we are going, yeah, so we check. So this is gonna be true, true. So for M, also, because m goes up to 5, so this is true, true, but this is going to be false and false according to this, because this is going to say, okay, let's look at just rows, m, not columns, and we'll get true if it's smaller than m, which is m is 5. So I guess only this one should get true. And if we are looking at the columns here, we'll give it true if it's smaller than n, and n is 6. Yeah, it's a bit confusing, but anyways, now we got true for this column, false, 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 and true, true, false, false, because these two are smaller than 6. It's confusing. And then this one is smaller than 5, and these, so these are gonna be false. It's just rearranged, you see, transposed a little bit. And then the mask, we get true and true. So this is the mask. We have this AND operation between each of these. Yeah, it's confusing. And true and true, true and false, true and false. Because you see, the first row always has true as the first element, and always has false in the other rows. So because you have false and something, then all of these rows will be always false. And then here you have true and true and true and true. So this mask will prevent it from trying to access memory places that are out of bounds for this matrix, 5 by 6 matrix. So because we are using tiles, blocks, so the first block 4 times 4, but this corner block down, bottom down, it's gonna extend, this 4 by 4 at the bottom down will extend over the map, so we will just access these two that are contained in the matrix. Then we also have this Triton ceiling division, which will divide two numbers and round up to the nearest integer. So if you divide 1000 by 256, you get 3.9 something. So output will be 4 of this ceiling division. Here you can check some of my other videos like FP8 quantization, and thank you for watching and see you in the next video.